All right, here we go. The related rates is our next big application of the derivative. We looked at curve sketching, essentially, how f and f prime and f double prime affect the graph. We looked at the optimization, and now we're looking at related rates. All right, so what is related rates? Well, of course, rates means what? How fast something changes, or how something, how much something costs, really. It represents a rate of change. And related means like brothers, sisters, right? They're somehow integrated in some system. So let's look at this little example right here. Something as simple as inflating a balloon, right? Here's my little balloon, little green balloon. And let's say that we're inflating it. That means that the air is going into the valve right there. As this balloon inflates before it pops, there are lots of quantities related to this balloon that are changing, right? Let's talk about some of the quantities as we inflate this that are changing. What's happening? The circumference is changing. Is it increasing or decreasing? Increasing. Yeah, the girth of it. I don't know if you want whatever you want to call it, right? The circumference is increasing. The balloon's getting bigger. Yeah, and that's it, right? What else? The surface area is increasing or decreasing? Increasing. Okay, cool. What else? The volume on the inside of air is increasing. What if we call that the radius of the balloon? The radius is increasing. The diameter is increasing. Anything else? The opacity is decreasing, right? You're stretching it so you're able to see through it. There might be others, right? We could probably get clever and say something else, but the pressure, right? The pressure inside is what? It's another one. Increasing. All of these are quantities related to balloon that are all changing, but they're not changing arbitrarily in relation to one another, are they? They are all changing at a rate that is related to each other. Yeah. And that's what this section's about. We're going to be given situations maybe as simple as inflating a balloon, and we're going to be asked to determine at a specific moment in time, because that's what calculus is, at a specific moment in time, how fast are any one of these quantities changing with respect to what? What's a pretty good independent variable in life? Time. Yeah. We're going to be using time as our independent, let me spell that right, as our independent variable. How fast all of these things change with respect to time. And it's going to turn out that most of our equations, like our equation for the volume of a spherical balloon, doesn't even have a t variable in it. It's not going to be a problem because we have implicit differentiation. Okay, so anytime we talk about something changing, it doesn't matter what the quantity is, with respect to time, we're talking about a rate of change at that moment. So that's going to be the derivative with respect to time of a quantity. So that's one important thing about related rate. Our independent variable is time. Another big part of this section is deciphering information that's given, because these are word problems, and then writing it in terms of some mathematical quantity, and that's the rates themselves. So we're going to start off on example 1 by writing these English sentences into mathematical sentences, and they all involve something changing. So example 1A, Mortimer. There's a guy named Mortimer. Mortimer is growing at a rate of 3 inches per year. Interesting. Now, that's kind of a vague sentence, right? Is he growing in confidence? Is he his belly getting bigger? Or is he getting taller? I guess we all have to agree on what it is. Wider? What did you say, Berkeley? Wider. You want to go with wider? It's kind of vague. We can say it. So Mortimer is growing widthwise, would say. This is kind of vague, and I left it vague on purpose so we can have this discussion. I thought you were going to say with confidence. At a rate of 3 inches per year. So what is it that's changing? What variable do you want to define Mortimer's width as? W, okay? So here's the thing. Every single rate is going to be written as d something dt. And a lot of the times you're going to have to define what that variable is. So let's go ahead over here and say W equals the width of Mortimer, or Mortimer's width, to not use the passive voice. So dW dt is going to equal, now the equal means is, right? And it's 3 inches per year. So that would be 3 inches per year. Now here's the most important part of these types of problems. Assigning, is there 2 S's in assigning? That doesn't look right. Yeah, okay. Assigning the correct sign, S-I-G-N, to the rate, or giving it the correct sign. And it's going to always come down to whether the quantity that you define, in this case the width, is increasing or decreasing, right? If the quantity is increasing, the rate is what? Positive or negative? Positive. If the quantity is decreasing, then the rate of change is negative. And it's going to always come down again to you interpreting the English word that's in the sentence. If the width is growing, then it's what? Increasing, and the rate is positive. Yeah. It's not a big deal if you forget to consider that if it's a positive rate, because most people, when they put 3, don't put -3 by default. They put 3. But if Mortimer was losing weight, losing girth, and you didn't put negative down, then you'd be in trouble. Okay? So there you go. This now says the exact same thing, very efficiently, mathematically. The WDT is positive 3 inches per year. All right, next one. My stock portfolio is losing 5 cents a day. Whew. I'm not going to change anything. I'm in it for the long haul. All right, so what's actually changing? The value, right? In coin units, what do you want to use? You want to use dollars or cents? Yeah, dollars. Okay, so let's let yen. Let's let what do you want to use for the value of my stock? The dollar sign as a variable? Okay, we'll let that be the value, the dollar DT. It's the value of the portfolio. Okay. So, the dollar sign, the dollar DT. Cool, I like it. It's a variable. We've never done this before, ever. Woohoo. All right, 5 cents per day. That's a rate, right? Cents per day. Cents per day. So that's 5 and the cent sign per day. Cool. Done, yeah? No. Because I'm losing 5 cents per day, the rate is negative. Yeah. There you go. Now that makes sense. Now it's kind of weird because I put the dollar DT, but my units are in cents. Is that okay? Yeah, because I defined the dollar sign to be the value, not necessarily in dollars. It's the value in cents, not dollars. Okay, cool. So when you're going from the English sentence to the mathematical sentence, it's super important that you get the sign, S-I-G-N, of the rate, whether it's plus or minus. Similarly, what we're going to be doing is like the cold yam in the hot oven. If you are given a math sentence like this and you're asked to describe what's happening, you would need to be able to interpret the sign as either increasing or decreasing, and then you can adjust the word by saying losing by the positive amount, whatever, with units, okay? So you always interpret the sign and then give the quantity as a scalar quantity without units. All right, the radius of a circle gets larger by 4 feet every hour. What do you want to call the radius of the circle? R works for me too. Yeah, so dr dt, that's the radius of the circle, gets larger by 4 feet per hour. So let's do it first. Is the sign of the rate positive or negative? Positive. So 4 feet per hour. You don't need to put a plus sign in front of it, right? Is it wrong to put one? No. If you want to like emphasize the positivity, you can put a plus sign. And if you're excited about it, could you put an exclamation point at the back? No, that's different. Okay, that's factorial in a math class. So anyway, 4 feet per hour, and it's positive. The outside temperature is dropping by 5 degrees Fahrenheit per minute. What's actually changing? Temperature. What do you want to call temperature? F for Fahrenheit. Okay, so dF dt. And let's see, by 5 degrees Fahrenheit per minute. So 5 degrees Fahrenheit per minute. Positive or negative rate? Negative, right? Dropping. The outside temperature is decreasing. Of course, you can refine that and say dropping. So there's a lot of different words in English that you could substitute contextually, depending on the context, that implies increasing or decreasing. When you're writing a sentence, though, I would encourage you pretty much just to use the word increasing and decreasing. All right, any questions on that? This is a very important part of setting up and evaluating a related rate problem correctly. Mortimer's width. Okay, here's a real easy example. The length of a rectangle is decreasing by 2 inches per second, while its width is increasing by 3 inches per second. This is a very typical type of problem that's handed to you. When you're given a rate of change, decreasing by 2 inches per second, it doesn't tell you for how long that rate is valid. So, what would you assume? Always. You would assume that that's a constant rate, unless it tells you like over some interval of time. So if it tells you that, assume that it's a constant rate. And the width is increasing by 3 inches per second. Now here's the follow-up part. When the length is 10 inches and the width is 6 inches, how fast is the perimeter changing and how fast is the area changing? So you can imagine that you're like a spectator and you bought a front row seat to this event. And the event is a rectangle that it's decreasing by 2 inches on one side and increasing by 3 inches on the other. And you're watching it, right? And it's exciting, and you want to share it on social media, so you have your what there? You have your camera with you. Right. And you know what's coming back now? Not just phone cameras, Polaroids. We got my daughter it's a Fuji film, but it's a Polaroid-esque film, and it's so cool and such a novel thing for her to actually take a picture and have it print out and develop. It's coming back. And yeah, and records are coming back. So, here's the thing. Let's say you have one of those throwback/new Polaroids, right? And you're right there. And you take a picture at a certain moment, right? And you capture it in time for posterity forever. Now, when do you take the picture? You take the picture when the length is 10 and the width is 6. Now, I don't know how you know that. Maybe they're calling out the length and width as it changes. But yeah, like an auctioneer. That'd be tough. But when it's that, you take a picture, okay? And so I call that your snapshot moment, all right? You're going to have to identify a snapshot moment. Because remember, calculus is the rate of change at a single point in time. But we're not going to refer to the time as generally as like when t equals 5 seconds or 2 hours into the event, right? It's usually going to be referencing a moment in time like this, when some of the dimensions are so-and-so. So here's what we're going to do. We're going to draw a picture, just like we do with optimization. It kind of helps understand what we're doing. It also helps you define your variables, which is pretty darn important. Any objections to L and W for length and width? We'll let W be the length and L be the width? No, we'll let L be the length and W be the width. Okay? Now, those two are changing. So here's the thing. In any problem, if something is changing, you want to give it a variable, right? That's what variables represent. If something is not changing, if it's a constant throughout the life of the problem, then you don't need to call it a variable. But L and W are changing. And I took a picture when L was 10 and when W was 6. There's my snapshot moment, and I like to draw that in a camera. Now, the flash cubes are an old thing, too. Those haven't come back yet. Yeah, my camera's upside down. It's stylistically, right? They used to have flash cubes, and you stick them in the top, and they make a weird sound, and then you take it off and throw it away and put another flash cube on there. So there's my flash cube. That's your snapshot moment. Okay, so here's what we want to do. The last part gives you the question, right? How fast is the perimeter changing at that moment? You want to give yourself a target, right? If you don't have a target and you start shooting, then you're never really going to know if you hit what you want. It gives you something to aim at. Your target is your answer. We want to know how fast the perimeter is changing. That's the rate of change of the perimeter with respect to time. What do you want to call the perimeter? What letter? P. Good. You didn't say hashtag. I'm going to let dPdt be my target. I'm looking for dPdt, right? The rate of change of the perimeter with respect to time. Well, I need to relate that rate of change of the perimeters to something else in the problem. Well, let's go back to the beginning. It says the length of the rectangle is decreasing by 2 inches per second. Well, what we did in the beginning is what we're going to do now. We're going to label our rates. So the length change is dl dt, and it's decreasing by 2. So is it plus 2 or minus 2? Minus 2, and it's inches per second. And notice since it's per second, that's how we know it's with respect to time. Units of length over units of time. And it also said the width is increasing by 3. So dw dt is going to equal what? Positive or negative 3? Let's see. The width is increasing while the okay, yeah, so it's positive 3. And again, if you didn't label the rate of change of the length as negative 2, your calculations are going to be RONG wrong in the end. So we now have these rates of change labeled, and here's where the problem gets its name. We would like to relate those rates to each other in this problem. We know they're changing at a rate related to each other. We want to relate the rates, but before we can relate the rates, we have to relate the quantities. Okay? So in a rectangle, how do I relate the length to the width to the perimeter? 2L plus 2W. There you go. That's one of the hardest things about, I guess, the related rate equations. What is that magical equation that relates the quantities so that I can then relate the rates to each other? If you're talking about like a rate of change of position, you have your kinematic equations, right? You have position, velocity, and acceleration. This is your quote-unquote position equation, if you want to think about it in terms of motion. It tells you the quantities at any given moment. If you know the length and the width at any given moment, you can find the position of the perimeter. If you know the perimeter and the length, you can find the position of the width, essentially what it is. What we're after is the quote-unquote velocity equation. We want to know how fast it's changing with respect to time. So, guess what we get to do now? We take the derivative of both sides with respect to time. And you can show it like that. Now again, notice our equation up here doesn't have t in it at all. Is that a problem? No. We know how to take the derivative implicitly. Every variable up here then that is not a t is going to have the chain rule applied to it, d variable dt. In fact, none of them have a t in it, so every single one of them is going to get a d variable dt. So here we go. What's the derivative of the left side with respect to t? What's the derivative of p with respect to t? Well, it's 1 times the chain rule, dp dt. dp dt, why? That's what we're looking for, right? It's the velocity of the perimeter, if you want to think about it that way. What's the derivative of 2L with respect to t? 2, right, times the chain rule, dl dt. That's the rate of change of the length, which we have labeled, plus 2w becomes 2 times dw dt. That's your rate equation. And all of your d rates dt, your d variables dt, those are the rate of change or the velocities of those particular quantities. All right, so now all we have to do is evaluate it, okay? It's already solved for dp dt. That's what we're interested in. So now we refer to the snapshot moment. okay? And you do want to refer to it. So let's just say when L equals what? What was the snapshot? 10? When L equals 10, we get dp dt, which is what we're looking for, equals. Now, in a formula, right, this is like a formula with 1, 2, 3 unknowns. Those rates are unknowns. You have to know 2 of the 3 unknowns. If dp dt is the one we're trying to find, I need to know what these 2 guys are. Do I know what they are? Heck yeah. In fact, I have them nicely labeled right there. So now we just plug them in, and we get 2 times dl dt, which is negative 2, plus 2 times dw dt, which is 3. And if we add those up, we get negative 4 plus 6, which is 2. And what are the units going to be? Here's where Leibniz notation is pretty awesome. It's going to be units of perimeter over units of time. Well, we measure perimeter in the same units we measure the length, which is in inches. And both of those are changing with respect to time in seconds. So that should be 2 inches per second. Now, it's interesting to note that the change in the perimeter only depended on how fast the length and width were changing, right? It didn't matter what the current size was, right? It's not a function of W or L. So we could say that the perimeter is changing at a constant rate, can't we? This is a constant, remember, and this is a constant, so dp dt is a constant. The perimeter is changing at a constant rate. If we had to write a sentence, though, and I'm just going to say it, not write it, like we did with the Koldian problem, you would reference the moment in time, and you can reference either the length or the width. When the length is 10 inches, comma, the perimeter of the rectangle is what? Increasing by 2 inches per second. Done. And that's actually a constant throughout the life of the problem. Well, there's another question here. Part B. We want to figure out how fast the area is changing. So I'm going to come up here where there's space. What do you want to call the area? A is good. So dA dt is now our target. Well, I want to somehow now relate the rates together. And I have all kinds of rates I can relate now. I can either try to relate the perimeter rate to the area rate or the length and width to the area. But before I can relate their rates, I do need to relate their quantities. If you can relate the quantities, you got it, because then you just take the derivative with respect to t. So in a rectangle, how can I relate the area to the length and width? It's so easy no one wants to say, right? It's LW. So you do have to come up with your equation. It's kind of like our primary equation for optimization. There is no secondary equation. You can have as many variables as you want here. So there's the area. This is your quote-unquote, again, position equation. You know what the area's position is at any given moment if you know its length and width. We want the rate equation, which is our quote-unquote velocity. I want to know how fast the area is going, right? So we're going to take the derivative next with respect to time, always. So what does the left side become? dA dt, right? And over here I get to use the, my favorite, the what rule? Product rule. Good. So we get dL dt times W plus L times dW dt. So that is conveniently solved for the rate quantity that we're interested in. It won't always be that, but in this case it is. Notice that I have 4 unknowns on the right. So if I want to know how fast the area is changing, I need to not only know how fast the length and width are changing, which I do, I need to know what the width and length currently are. So the area's rate of change does depend on the current length. Well, here's where the snapshot moment really comes in. I know what W and L are both at that time, right? So let's go ahead and do the same thing we did. When L equals 10, we're going to evaluate. When L equals 10, dA dt equals, and now we just plug in very carefully. dL dt was -2. W at the moment, this is where your snapshot moment comes in. You don't plug these in before you take the derivative, only after. W is 6 plus L was 10, and dW dt was positive 3. Now, if you simplify that, you get negative 12 plus 30, which is 18.
All candidate information, including the application, references, and documentation of service hours, are due on or before Friday, January the 8th. Again, that's all of your candidate information is due before Friday, January the 8th. Please see Ms. Gray in room 103 if you have any questions.
Yep.
And teachers, at this time, please turn your TVs to channel 4 for the morning announcements, or you can view them on your iPad at VHSTV.com.
Okay, so you simplify right here again, and you end up with 18. And if you're not sure of the units, there's two ways to get it. You can always refer back to what you're trying to find. The ADT would be units of area over units of time. Go back and find what the units were, area units or square inches in this case, and time is seconds. But if you actually include your units in your computations, it'll actually work out that way, because dLdt is measured in inches per second, right? And W is measured in inches. So we have inches per second times inches, which is square inches per second plus square inches per second. Those are like terms. You're going to get square inches per second. So you can do a little bit of stoichiometry, right, in your calculations if you're not sure. And the sentence would be, let's see, who wants to take it? When the length is 10 inches, comma, per second. Good. The area is increasing by 18 square inches per second. Is this also good in the very next instant? Like the rate of change of the perimeter? No, because the rate of change of the area depends on what W and L currently are. So that's why the snapshot moment is important. Sometimes it doesn't matter. It depends on what's being asked. There are other things maybe that we could look at with the rectangle to see how fast it's changing, but I think you got the idea. These are like physics problems, but instead of just motion, we're talking about rectangles. Exciting. All right. What's more exciting than a rectangle? All right, triangle. Whose sides are changing? It's the event, right? I guess the rectangle is just the opening event, right? The opening act. And here's the one that we're interested in looking at. You want to work it, or you want to go to something more meaningful? We bought the ticket to the event, right? Might as well stay. Yeah. All right. Let's see if we can squeeze this one out here, at least part of it. A right triangle. Okay. So right when I read that, I'm going to go ahead and just draw a right triangle. There it is. Its sides are changing. Okay. Okay, that's good. They have sides of 30 and 40 inches at a particular instant. I'm not sure which one is which. I'm going to call that one 30 because I drew it smaller. I'm going to call that one 40. But they're changing, so I need to give them variable names. What do you want to call them? Base and height. Okay, so B and H. I like that. If they're changing, you have to call them variables. But I really have my snapshot moment now when B is 30 and H is 40. You don't have to draw the camera. I'm just used to it. Okay, that's your snapshot moment. If the shorter of these two sides, so that's when B, right? That's the shorter one I've labeled B, is increasing at 3 inches per second. So immediately when I see that, I'm going to call that dB dt. I'm going to label my rates. And is it positive or negative 3? Positive 3. And we can assume that's a constant. And the longer side, which I'm calling H, that's dH dt's rate of change. It's decreasing by 5, so that's negative 5. How fast is A, the area, changing? All right, so part A. The rate of change of the area, I'm going to call dA dt. I've got all my essential elements already right there. I've got my picture. I've got my variables labeled. I've got my snapshot moment identified. I've got my given rates labeled with the correct sign. And now in part A, I have my target. So here we go. I want to relate the rates to each other, but first I must relate the quantities. So in a right triangle, how do I relate the base and the height to the area? 1/2 base times height. So you do have to know a couple of these formulas. That one's an easy one. That's your quote-unquote position equation. Next step is always to do what? Take the derivative with respect to time. So we get dA dt equals product rule again. 1/2 dB dt times h plus 1/2 b times dH dt. Now, it is convenient, once again, that our rate equation has explicitly been solved or is solved for dA dt. So if you look at the right side, once again, we have 4 unknowns. And to evaluate it, we need to know those 4 things at that given moment. Do we have them? Yeah, we have them. So here we go. You do want to reference the moment in time. So how about when b equals 30, we get dA dt equaling 1/2. And now it's just carefully plugging in the right quantity. dB dt is 3. At the moment, h is 40 plus 1/2 times b, which is 30 at the moment, times dH dt, which is -5. And if we simplify that, we get 60 minus 75. So that's -15. And what would the units be? Yeah, inches squared per second, I believe. Yep, we're talking about inches in second. So when the base is 30 inches, comma, the area of the right triangle is decreasing by 15 square inches per second. Last one of the day, part B. How fast is the hypotenuse changing? Ooh, well, what do you want to call the hypotenuse? We can't call it h because we call that the height. X? X. X. Okay, I like it. Is that what you said? What did you say? Georgia Bulldogs? No? S. How about S? But I'm going to put my script letter S because otherwise my S looks like a 5. Okay, so if I label the hypotenuse S, now on part B, you can call it X or whatever. We're looking for the rate of change of the hypotenuse, so we're looking for ds dt. That's our target, right? Now, before I can relate the rates, I need to relate the quantities. So how do I relate the hypotenuse to any of the other quantities in here, namely the h and the b? Yes, the Pythagorean theorem, right? So here we go. S squared is equal to b squared plus h squared. Coming up with that equation is kind of the hardest part of related rates. You need to find the equation that relates the quantities to each other. It's usually going to be some kind of geometric formula or some type of like similar triangles or a Pythagorean theorem. But there you go. Now, it's not solved explicitly for S. Is that going to be a problem? Do you want to take the square root of both sides and solve it for S? We're taking the derivative implicitly anyway because we're taking the derivative with respect to t. So you might as well just leave it as S squared. It'll make the computations a little bit easier because you don't have that 1/2 radical on the quantity. So here we go. We'll take the derivative now. What's the derivative of S squared with respect to t? 2S times the chain rule ds dt equals, on the right, we get 2b dB dt, which was a rejected Shakespeare line, plus 2h dH dt, which was also rejected, even though Hamlet was in favor of that because it had his letter in it. Now, there's your rate equation. You could simplify, right? What do you notice all the way across that we can divide out? 2's, okay? Simplify early and often. Now, notice this one is not solved for anything in particular. We're looking for ds dt. So this is a literal equation or a formula. If you want to divide both sides by s so that it's explicitly solved for ds dt, you have at it. I'm not going to stop you, but I'm not going to make you either. In fact, I wouldn't do it. I would solve after I plug in. Okay? So here we go. I think we're ready to plug in when b equals 30. And we'll stick with Clemson colors here. All right? Good. I know who you're rooting for next Monday night. Yeah? When b equals 30. Let's see. We need to know what S is at the moment. The first one I got to plug in. At the moment, what is S? I haven't found it. I've already taken the picture, and I know 2 of the 3 sides of the right triangle at that moment. Being a good mathematical detective, from the evidence that I've gathered, namely the photo, can I determine what the hypotenuse was at that moment? It was 50. Ah, good detective work, right? It's a 3, 4, 5 right triangle magnified by a factor of 10. But if you didn't know that, guess what? Your position equation right here, it relates your quantities. So you could plug it in and solve. So sometimes in your rate equation, you have to go back and gather things. So here we go. We get 50 times. We're not going to be able to finish, but you're going to get the idea. You're going to plug in everything that you have, and you should have everything at this point. 30 times dB dt is 3 plus h, which is 40, times dH dt, which is negative 5. And now you would just divide everything through by 50, and I'm going to do that with the magic of notability. There we go. And, of course, the units are going to be inches per second because we're back to hypotenuse. That's a related rate problem, right? Not that bad. Not that bad at all. In fact, it's kind of what? Fun, yeah. We could probably just take the word kind of right off of there. It is fun. Yeah. Okay, we'll quiz on Thursday, not tomorrow. Have a good rest of the day.